Welcome to The Explainer. I am so incredibly thrilled you're here today because honestly, we are about to pull back the curtain on one of the absolute greatest magic tricks in modern technology. We are diving deep into the architecture of multi-threading to reveal exactly how your computer seemingly manages to do a million things at once. Okay, let's just dive right into it.
Think about your workflow right this very second. How does your machine download a massively heavy file in the background, play a crystal clear, high-definition video, and let you furiously type out notes without missing a single solitary keystroke? I mean, it really feels like it's all happening at the exact same time, right? Well, as we'll uncover today, that feeling is actually a brilliantly orchestrated illusion.
So here's our roadmap for this explainer. We'll start with the multi-threading illusion, then compare concurrency versus parallelism, hit the speed limit known as Amdahl's law, look at user versus kernel threads, tackle some real-world development challenges, and finally wrap up with Linux tasks and future openings.
All right, Section 1, the multi-threading illusion, breaking down the core components.
To really understand this illusion, we have to introduce the fundamental unit of CPU utilization that actually makes all of this possible, and that is the thread. Let's use a quick analogy. Imagine a computer program, which we call a process, is a super busy restaurant kitchen. The chefs? Well, they're your chefs. In a single-threaded process, you just have one chef doing literally everything. But in a multi-threaded process, you've got a whole team of chefs. Now, they all share the exact same kitchen space, the same recipe book, and the same pantry, which in computer terms corresponds to the code, the data, and the files. But here is the crucial part. Each chef gets their own personal cutting board and checklist. Those are the registers and the stack. This setup allows them to work together super efficiently, but keep in mind, there's absolutely no physical protection between them. If one chef accidentally spills soup all over the shared pantry, the entire meal is ruined for everyone.
Moving right along to Section 2, concurrency versus parallelism, defining execution types. Okay, so let's tackle one of the most essential questions in this space. People in computer science constantly confuse two very vital terms, concurrency and parallelism. Let's clear that up right now. The absolute crux of the matter is this delineation. Concurrency is about making progress on multiple tasks. It's really about structure. A single processing core uses a scheduler to rapidly juggle tasks. Parallelism, on the other hand, implies the system is performing more than one task literally at the exact same time. It's about physical execution across multiple hardware cores.
Picture it like this. On a single core, it processes task 1, then task 2, then task 3, and it's switching back and forth so incredibly fast that to you, the human sitting at the screen, it looks parallel. But it is a total illusion. That is concurrency. Now, with true hardware parallelism, Core 1 is actively grinding on its tasks, while Core 2 is simultaneously grinding on completely different tasks in that exact same fraction of a second.
Which brings us to Section 3, the speed limit, Amdahl's law.
So you might be thinking, hey, if multiple cores give us true parallelism, does that mean we can just add infinite processing cores to our computer and get infinite speed? Well, the short answer is a resounding no. And the reason for that is Amdahl's law. This is a formula that identifies the absolute maximum performance gains you can achieve by just throwing more cores at a problem. The completely counterintuitive reality here is that virtually no application is 100% parallel. There's almost always a serial portion, a chunk of the code that absolutely must run in sequence, one step right after another. And that serial portion, it fundamentally bottlenecks your overall performance.
Let's put some concrete math behind this. Say you have an application that is wonderfully optimized. 75% of it can run in parallel, and only 25% is serial. If you upgrade your machine from 1 core to 2 cores, you do not double your speed. You're not getting a 2x speedup. According to Amdahl's law, you actually only get a 1.6x speedup.
And when you look at how this builds as we scale up, the reality sets in. Imagine charting this out. A perfectly straight, upward-sloping line would represent the dream. Ideal, linear speedup. But if you have an application with, say, a 50% serial portion, it doesn't matter how many processing cores you add. 4, 8, 16, it literally doesn't matter. The performance gain just asymptotically hits a total brick wall. It just flattens out. This is a pretty harsh reality check for software engineers. Infinite hardware simply cannot solve fundamental software limitations.
All right, Section 4, user versus kernel threads, the mapping models.
So how do our user-level programs practically communicate with the hardware to actually manage all these threads? Well, the operating system kernel is the ultimate boss of the hardware, and user applications sit right above it. we have to map our lightweight user threads down to the heavy kernel threads. Let's step through how we've done this historically. First up is the many-to-one model, used by early systems like Solaris Green Threads. You map many user threads down to just one single kernel thread. It is highly efficient for the user library to manage, but there's a pretty fatal flaw here. If one single user thread makes a blocking system call, say it's waiting for a file to download, that single kernel thread blocks, and boom, the entire process freezes. To fix that freezing issue, OS developers moved to the one-to-one model. This is what modern Windows and Linux primarily use today. Every single time you create a user thread, it creates a dedicated kernel thread. This provides fantastic concurrency. If one thread blocks, another can just keep on running. But what's the catch? Kernel threads are expensive, like really expensive. They require a ton of memory and management overhead. If you create too many of them, you will absolutely crush the performance of your entire system. Because of that, developers conceptualized the many-to-many model. This is essentially the holy grail of threading models. It allows many user threads to be dynamically multiplexed onto an equal or smaller number of kernel threads. It lets the operating system dynamically balance the load, creating only exactly as many expensive kernel threads as the hardware can actually support. It gives programmers the total freedom to create threads without constantly sweating over crashing the kernel.
Section 5. Real-world threading issues, development challenges.
Now, when you transition to the practical challenges of orchestrating these environments, communication gets incredibly thorny. When you have all these chefs in the kitchen, things get super complicated. For instance, if a process creates a duplicate of itself, does it duplicate all of the threads or just the one that made the request? When the OS sends a signal, like a user desperately mashing Control-C to stop a program, which specific thread out of 100 actually receives that signal? And what if you need to cancel a thread right in the middle of its execution? Do you just kill it asynchronously, potentially leaving shared data completely corrupted? Or do you defer it, politely asking the thread to clean up and exit when it hits a safe checkpoint? These are the really complex architectural puzzles engineers have to solve every day to make your software stable.
And finally, Section 6, Linux tasks and future openings.
We've talked a lot of theories so far, but let's see how a massively popular operating system practically handles these paradigms. Here is a totally surprising and fascinating insight. At the kernel level, the Linux operating system actually completely abandons the word thread. Yeah, it doesn't differentiate between a massive process and a lightweight thread at all. Instead, Linux treats absolutely everything as a task.
Linux pulls this off through a brilliant system call named clone. When you spawn a new task, you pass it very specific software flags that precisely dictate exactly what the new task is going to share with its parent. For example, if you pass the flag clone_VM, they share the exact same memory space, acting just like our traditional definition of a thread. But if you don't pass those flags, it acts like a completely separate, isolated process. It's an incredibly elegant, highly modular way to handle all the chaotic complexities of concurrency.
Which brings us to our final takeaway for today. We have seen the brilliance of threads, the illusion of concurrency, and the absolute hardware limits defined by Amdahl's law. But let me leave you with this really provocative thought. As we enter an entirely new era of massive parallel processing, think modern GPUs with thousands of individual cores built specifically for AI, does a decades-old formula like Amdahl's law still properly account for contemporary multi-core system architectures? Or are software engineers eventually going to figure out some clever way to break the speed limits we just learned about today? It's a hugely fascinating open question for the future of computer science. Thank you so much for joining me on this explainer, and remember to always keep questioning how the magic works.